The Apollo missions marked an historic moment in human history, with 12 astronauts walking on the lunar surface between 1969 and 1972. But for over 50 years, no human has returned to the moon. Now a new era of space exploration is taking shape. NASA's Artemis program aims to land astronauts on the moon in 2027 and establish a lunar space station in orbit by 2032. Meanwhile, China is also making bold strides, planning to put astronauts on the moon within this decade and develop an International Lunar Research Base in the 2030s. The catalyst for this renewed race to the moon was a groundbreaking discovery which Professor Mahesh Anand and his team at the Open University contributed to. There's been a reinvigoration of interest in the moon. Is that connected with the discovery of water on the moon?
We would like to think so, because water in space exploration is really unparalleled. I mean, it is such a resource that we cannot put any money on, because we need water for humans to survive on. This discovery of water, whether on the lunar surface or inside lunar rocks, has brought about this renaissance in lunar exploration. First of all, it's going to provide us resources as it is, and then humans are going to use the moon bases as test bed for actually practicing technologies, practicing living there, working there, so that then they can go beyond it and make more scientific discoveries. So yes, I think this is a paradigm shifting moment that we are living in.
Very interesting. It's a very soft surface, but here and there where I plugged with
The Apollo missions returned 2,200 samples, totaling 382 kilograms of lunar soil and rocks. Tests revealed no sign of water, and it was concluded that the moon must be completely dry. Fast forward 40 years, and scientists like Professor Anand decided to revisit those samples.
With the modern advanced technologies, actually we can now detect that tiny quantities of water. And remember, I'm saying water, but I'm simplifying it, because water is nothing but H2O. And therefore, what we are actually detecting most of the time is hydrogen. And when hydrogen is detected, it is expected that it is attaching itself to an oxygen atom. And when two hydrogen attach themselves to an oxygen atom, you have H2O, which is what we call water.
So just to be clear, it's not exactly liquid water that has been discovered, but the elements that form it. Hydrogen and oxygen found within lunar rocks can be extracted and combined to form water. Can I see some of the samples?
Of course, let's have a look.
moon rocks. Very excited.
Would you read out the label for me, please?
One, which was 11,
Yes.
Apollo 11.
The 20th rock collected,
Right.
the Apollo 11,
Yeah.
and then 246th time it has been split.
Wow. Oh, goodness me.
Yeah, and what you see there is a thin slice of that particular rock. So this is a basalt. So
Yes.
basalt forms when a magma erupts on the surface, cools down. It's a solid rock. So this is a slice of that solid rock collected during the Apollo 11. And in this rock, you have minerals, and those minerals are the one that are target for our investigations where we are trying to detect water. Because there are certain minerals in this rock that actually hold on to that water more so than the other.
As well as minerals that contain both hydrogen and oxygen, some lunar rocks contain minerals from which oxygen can be more easily extracted.
One special thing about lunar rocks, or particularly the basalts, is that they contain a mineral called ilmenite. And that is a compound of iron, titanium, and oxygen. And it turns out that near side of the moon, all those dark patches that you see on a clear night are made up of these basalts, which are rich in this mineral, ilmenite. And because ilmenite has been proven to be energetically much easier to react with hydrogen to extract its oxygen, and you just elevate the temperature, and at elevated temperature, those ilmenite, they very easily release their oxygen in the presence of hydrogen. And as soon as the oxygen is released, it combines with the hydrogen there, and it comes out as water, and you can collect it.
The best way to see the makeup of this lunar sample is under a microscope.
It's the same type of slice that you saw early on. So please have a look and tell me what you see.
Okay. Well, the first thing is it's really beautiful. And the second is I know this is silly, but I kind of feel like I can see where the water's hiding.
So here we are looking at a digitized version of the view that you just saw live under that microscope.
Yeah.
And the first version that you see here is called reflected light version,
Yes.
where the light is being reflected from the surface of the sample.
Right.
In this case, we are looking at the brighter grains. These brighter grains are of a mineral called ilmenite, which is a compound of iron, titanium, and oxygen.
Which is the one you're excited about.
Yeah, this is one of the key target minerals that will be used to actually create a reaction so that the oxygen can be extracted from it to combine with hydrogen to produce our water.
To get water.
But the other minerals that this rock is made up of, they're allowing certain degree, different amounts of light to pass through. And when the light reaches our eyes through these different minerals, it creates a display of colors. And those colors is what you see in this view.
Wow. I don't know why, but I think of this as the Wizard of Oz view. It's so beautiful. And
it's absolutely marvelous.
I've got to remind myself, I'm forgetting that I'm looking at a sample that's come from the moon.
Yeah, this is a rock from the moon, and not just from the moon. This is over 3 billion years old. Yeah, 3 billion. Yeah. And the entire history of life that we know on Earth is only 500 some million years. Right? So 6 times longer.
After the Apollo missions, a robotic Soviet mission collected a small amount of moon samples in 1974. It was then another 44 years until the China National Space Administration's Chang'e 5 mission returned samples in 2020. The Chang'e 6 mission in 2024 was the first to retrieve samples from the moon's far side by scooping with a mechanical arm and drilling down 2 meters into the lunar substrate. It returned nearly 4 kilograms in total. Some of these samples were studied by Professor Wang Jun Chang's team at the Ningbo Institute of Materials Technology and Engineering. They found a way to heat lunar regolith with concave mirrors to extract hydrogen and make water. Their method could create 50 kilograms or litres of water from 1 tonne of moon rock. As well as extracting water from lunar rock, recent remote sensing data has shown water could be present in the form of ice, as you would find in your freezer. This so-called water ice is believed to be near the moon's north and south poles, the next targets for the Chang'e project. Professor Zhang Fan is involved in designing astronomical experiments. Professor, why are the lunar poles so important?
The reason why the South Pole and the North Pole actually equally are interesting is that some areas on the moon, if you're on the pole, it's always sunlight. Which means if you have a base there, you get solar power all the year through, so that's good. And also, if you have a crater there, it's deep enough, because the sun at polar regions, they're at really low angles just above horizon. It doesn't actually shine all the way down to the bottom of the pit. So it's really cold there because there's no air, there's no convection to conduct sort of heat. So if you avoid the sunshine, it's cold. It's cold means you can have water ice there.
The Chang'e 7 mission, launching in 2026, is another unmanned robotic research spacecraft. It's planned to land on the illuminated rim of the Shackleton Crater, almost at the moon's south pole. That's further than any lander has been before. It aims to look for water ice and other resources.
So that's a surveyor mission. That's basically setting, just looking at the region where you want to set up the base. And it has a lander, a rover, just move around on the surface. And it also has a flyover probe, like a drone that flies over the craters. So you can look down to see whether there's actually ice. So looking for water is the most important thing that the Chang'e 7 would do. It will contain sort of a proton detector and spectrometer. Those are both looking for water.
If the mission confirms water ice is present, it opens the door to China building the International Lunar Research Station. I kind of know the answer to this, but tell us why water is so important for a permanent base on the moon.
So we need drinking water to begin with. And then water can be broken down by electrolysis into oxygen and hydrogen, and we can breathe the oxygen. So that's another life-sustaining quality. And also, once you have hydrogen and oxygen, they can be used as fuel and oxidizer for your rockets. So if you want to go to Mars, you can refuel on the moon. The reason why you want to do that extra step of going to the moon is because Earth is really large, it has a strong gravity, and it has a thick atmosphere. So your rocket launching from Earth, it needs to fight against the gravity, and it really needs to punch through the thick atmosphere, and that's really expensive. So from more immediate human presence to the longer term using the moon as a gateway to further explorations, water will both be very important.
And it's called the International Lunar Research Station for a reason?
There's always been this international collaboration, and more interestingly, besides the more established space powers, a lot of developing countries are getting their foot in the door in terms of space exploration through the Chang'e program. And for the future research station, it's actually stated that they're looking for something on the order of 50 countries to get involved. So it truly will become international, as the name suggests, International Research Station.
Chang'e 7 will carry a total of 21 tools or instruments known as scientific payloads, including 6 international payloads from Egypt, Bahrain, Italy, Russia, Switzerland and Thailand. On the outskirts of Rome, Dr. Simone Dell'Agnello has built one of the instruments that will be carried by Chang'e 7.
So this is called LARA. LARA stands for Laser Retroreflector Array.
Laser Retroreflector Array.
Exactly, that is the acronym. So it's an array of 8 mirrors,
Yes.
small mirrors, and it's used to measure the position of the device itself with a laser. So it's a time of flight measurement. There is a laser somewhere on Earth or on a lunar orbiter, which shoots the laser to the reflector, which is on a lander, for example, like Chang'e 6 or Chang'e 7.
Yes.
And then these special mirrors are called prisms. They are very similar. Actually, their working principle is identical to the ones that people use on Earth to measure bridges, houses, roads, etc. And they send the light exactly in the same direction it came from. So in this sense, they retroreflect.
And so that's where the retro comes in.
Correct.
Now I understand like Chang'e 7 is going up there to find out more about water on the moon, for example. Why do we need to know precisely how far away we are at that point?
Positioning on the moon is very important because one of the uses of this is to locate precisely the device and therefore also the lander. Okay? If you have more than one, then you can make a geodetic network. So you can, from orbit, navigate among these landers and rovers which do prospecting of the water, position yourself as you fly among these reflectors. But most of all, you can also go back to one specific place and use these for landing. It's called in jargon laser-based landing. So you may know that when you land, you have very often a scanning laser, which tells you if there are obstacles, big boulders or depressions, craters. So you want to avoid that, and you do that in real time with a laser. So a device like this is very, very useful because it allows, with a laser, to tune your position, your landing position, very, very accurately.
The device has 8 small prisms, each made up of a special arrangement of mirrors.
This is the same working principle. It's a retroreflector, much bigger one. So in this case, you should be seeing that the center of your optical camera is at the center of the edges of the reflector. Now, the reflector has 3 physical edges. It's a corner of a cube, okay? So you have 3 edges, but you see 6 in this case, because each edge is reflected by the front, the face which is opposite to it.
The 3 back faces of the mirror are arranged like the corner of a cube. When a laser beam enters the retroreflector, it bounces off each of the 3 mirrors in sequence. And this is the important bit. The outgoing beam is parallel to the incoming one, sending it directly back to its source, regardless of the angle at which the beam hits. This is why, whichever way the retroreflector moves, you can always see the centre of our camera lens. So here's my next question, and I think you've already answered it. I'm firing a laser from up here, but I'm in a moving body. I'm in a satellite that's moving, right? So when the reflection comes back, light is fast, but it's moved a little bit. How do you capture that returning light?
Neil, you are the first journalist. In 20 years, I do this kind of interviews or conversation to ask this question.
That's definitely going in the film.
This is a very technical question. It's the very first thing you have to take into account when you do this business. So there are two ways of doing this and compensating for velocity aberrations. One, given a fixed diameter, change the aperture of the back faces by a tiny amount. The other one is to increase or decrease the aperture of the reflector. So if you increase the aperture of the reflector, the light goes back more collimated. If you decrease, you make smaller the retroreflector, then the divergence increase.
Which means it can be caught by the thing that's moving
there is a
forward.
larger probability. So when you do this, unfortunately, you throw away light because you do that in a cone. So you catch only the portion of the light which goes forward, which will catch the orbiter in that case. And then you throw away the rest of the light. But there is no other alternative than that. So, very good question.
Thank you very much. The upcoming Chang'e lunar missions will rely on precision technology like this in the years to come. Professor James Head was involved in the Apollo missions and knows how complicated moon exploration can be.
Both the North and South Pole are really hard areas to explore because of the low illumination geometry, and it's just really difficult. The Apollo missions were in the equatorial and mid-latitude regions to avoid that harsh kind of like setting and temperature differences and illumination condition differences, etc. You got shadows all over the place. You got the permanently shadowed areas, but also these other ones, and they're cold. They're really cold. So, being able to maneuver in real time, and of course it's changing with time while you're on the surface. So it makes the exploration really, really complex. You need to be safe. You don't want to freeze your foot or whatever. It's challenging. It's pretty challenging.
To help prepare astronauts for future missions, the German Aerospace Centre has opened its new lunar facility. This recreation of the moon on Earth will help astronauts like Matthias Maurer train for the harsh conditions they will encounter at the South Pole.
And so stepping into Luna in the morning, I see all this and I think, okay, how will it be when humans will walk again on the moon? You see what you will see on the moon. You see rocks that are identical of the composition as on the moon. You see the sand as on the moon. You see a relief and the light conditions as on the moon. And since we will be flying to the South Pole area, the light will be very low on the horizon. And that's what we have here. And you see dark and long shadows. And these shadows are so hard, purely black, so you cannot see anything inside. Also inside we have a very deep area where we can drill into, because in the future we want to take samples where we expect that frozen water will be mingled and mixed with the sand. So we can drill into frozen sand here in Luna, and nobody else on planet Earth can do this.
China is also training their taikonauts with a specially built space environment simulation facility. The vacuum chamber contains an electron gun which negatively charges dust so it behaves as it would on the surface of the moon.
The solar system and the cosmos is a huge place, and no one country, person, or anything like that, or even collection of countries can explore the whole thing. And I think that's one of the nice compliments of the US and the Chinese space program and the European space program is that they're going to different objectives and approaching it in complementary ways.
Collaboration will be needed to set up permanent bases in such severe conditions. The Outer Space Treaty, signed in 1967, prevents any country from claiming sovereignty over any celestial body, and states space is to be freely explored and used by all nations for peaceful purposes. And there is another difference about this new push for the moon. Private companies are also involved. In the UK, a small satellite manufacturer is helping with communications infrastructure. Surrey Satellite Technology was founded in 1985 by spacecraft pioneer Professor Sir Martin Sweeting. The Apollo missions were very much a geopolitical event. They were about who was more dominant, the United States or the USSR. What's going on today?
I'm actually a child of the Apollo era because I watched the moon landings when I was a early teenager, and that's what stimulated me. But things have really changed a lot because, first of all, space now includes much greater participation of the private sector. It was, in the early days, primarily a geopolitical, very strongly military-inspired exploration and activities in space. But in the last decade, the private sector has taken an interest in this because they see the potential for a lunar economy, and also supporting some of the government aspirations for long-term lunar bases. And so the whole thing has changed. And yes, there is a bit of a race because there are now lots of players that are all jostling to participate in this.
I was fascinated to hear you use the phrase the economy of the moon. It sounds like it's going to be a very busy place.
Well, if you have a look over the next, I think, 10 years, there's something like 100 different missions being planned to go around the moon, some of them on the moon, either for exploration or for scientific purposes, and the potential for an economic activity on the moon. Now, exactly what that's going to turn out to be and how profitable it will be and what sort of economy is going to support, I think is probably an open question at the moment. But the potential for that is seen particularly by the private sector.
How does what you're doing here fit into all of that?
Well, this is a very, very small bit of what which we're trying to contribute into this. And the first, we have a mission called Lunar Pathfinder, which is a first spacecraft which is going to provide commercial services around the moon. So if you think about it, you have mobile phone networks and you have navigation satellites providing us with navigation on Earth. We're going to need the same on the moon. Every crater looks much the same on the moon, so you're going to need your GPS or your Beidou on the moon to be able to find your way around. And the whole purpose of Lunar Pathfinder is to create the opportunity to see how all of this works and to make the first steps and to learn, because I'm sure we won't get it all right in the first instance, and of course to provide services to other international players.
International, such as China? How does China fit into all of this?
Well, of course, China has a very ambitious and capable lunar exploration program. They have the Chang'e 4 and, of course, its predecessors. They already have a relay satellite, and we would like to see, if possible, collaboration with China on this and providing perhaps additional services to support their ambitions, as well as other international players.
Sir Martin Sweeting sees future lunar bases modelled after those in Antarctica, where nations establish independent facilities while fostering coordination and collaboration supported significantly by private enterprises. The SSTL Lunar Pathfinder satellite will be the first of a constellation of interconnected lunar orbiters that will provide data relay services for communication and navigation around the moon. So Lily, where are we?
So we are currently in the AIT clean room.
Which is why we're in this glamorous outfit.
And you do look fabulous.
Thank you very much.
And this is Lunar Pathfinder.
Forgive me, but it looks a bit like a flat pack satellite.
Yes, you'd usually expect it to be in a bit more of a boxed state.
Yeah.
But imagine the origami cubes you used to make as a child. You sort of fold it all up and it all
So this is
clips
going
together.
to come up here.
Yep, and this one will come up this way.
Right.
And then we'll have a base plate, a top plate, and then a solar array closure panel that will go on the front.
These buttons, I know they're not buttons, but they're fascinating. I really want to touch them.
Please don't press them.
What are they?
These are our star trackers. So they'll look out to constellations. They'll be loaded with a specific map when we launch, and then they'll look at the angles off those stars. Almost like, imagine what you had on ships in medieval times, where they're looking at different sextants with their stars. and it'll be doing that in the module.
So what's this magnificent beast here?
So this here is our onboard computer and the data recorder, so the brains of the spacecraft.
And how do you control the attitude of this thing when it's in space?
So we have two methods. We'll firstly be using a propulsion system, and secondly, we'll also be using our normal AOCS, or attitude orbital control systems, such as reaction wheels and gyros.
Can we see one of those wheels?
Oh yeah, absolutely. So we've got this is the mass dummy of one of our wheels.
Oh, that's quite a lot of mass. That's about 3 or 4 kilograms.
They're rather heavy.
Yeah.
And then we'll have 4 of those distributed across the spacecraft.
So that goes, if you move that like that, the inertia of this changes the attitude of the spacecraft.
Yes, so this itself will stay still, and then there's a sort of a wheel inside it that will be moving.
Oh, so this isn't the final thing?
No, this is just the mass dummy.
A mass dummy oh, right, yeah. I understand.
If it was a real thing, we wouldn't be handling it in this way.
Ah, good point. When I look at this, I'm getting a real buzz out of thinking this is going to be in space in what, 2 years?
Yes, around that.
How does it make you feel?
It's extraordinary. Every job has its highs and lows, and sometimes you're sat behind the computer screen sending emails or in a meeting, but then you come down here and you go, this is going to go around the moon. And then you'll leave at the moment because it's winter. You'll leave and the moon's up and you go, that's where it's going. It's going to the moon, and you just have to pinch yourself ever so slightly. Really quite cool.
Professor Sweeting talked about an economy on the moon that this will contribute to, helping people communicate, helping people know where they are. If you had the chance, would you go and join that lunar economy?
I'd be in two minds. Part of me would say absolutely yes, because if you're given the chance to go to space, why would you say no? But secondly, I don't think I could leave my dog behind.
Not to mention it would be terrifying.
It would also be terrifying, yes. The launch itself, it's difficult to go to space. But if you can help put forward for the human race, as we move on to the moon, and then through going to the moon, looking forward to going to Mars.
Do you see the future of the moon, or even space in general, do you see that as collaborative or competitive?
The future, it has to be collaborative regarding agencies and getting everyone to pull forward in the same direction. There will always be a side of competitiveness within the commercial market. If you don't have small companies working against each other to better each other, then you won't develop the technologies with the speed and agility that you need. But it's the agencies collaboratively. We just have to work together to work along these same frequency guidelines, space recommendations, outer space treaty, for example. And that's where we need to be collaborative, because we are, tiny human beings on a rather small planet orbiting a sun in a solar system that doesn't really see us. So we need to remind ourselves we need to work together to make sure that we are all pulling in the same direction. It has to be collaborative.
There's a huge amount of interaction between American scientists, Chinese scientists, and international scientists. I mean, science is just fundamentally an international endeavor. It's so incredibly more true for space because it's huge, and we need all the help we can get.
All of these projects have a shared dream of redefining humanity's cosmic boundaries. And the moon, our closest celestial neighbour, shining in the night sky, has always been an inspiration to all of us.
The sky is, I think, is almost always associated with some sort of deity, and having such a prominent thing so bright in the sky, the moon, has to be important. People have this spirit of exploration, and they say the space is the final frontier, and the moon, obviously, being so close, would be the first step.
It makes us realise that the universe is bigger than our flat Earth. And you look up and you see this, and it gives you the inspiration and say, look, this has been there ever since the dawn of mankind. We're still looking at it, but now we have the opportunity to go and touch it.